We're going to talk about how we would find the surface area of a solid of revolution. So first of all, let's consider some solids and think about surface areas. What if we had a cylinder of height h and radius r? So we could take this cylinder and we could think of unwrapping it to see how it was put together and essentially what materials it would take to build this cylinder. So as we unwrap it here, we can see that we end up with a rectangle for the piece that was wrapped around, and then the top and the bottom are both circles. So as we look at this rectangle, when we unwrap this, we can see it would have height h, but we can see that the length as we unwrap this is going to be the distance around here, which is the circumference, which is 2 pi r. So this would tell us what it would take to build around the thing, and then each end, top and bottom, would be a circle of pi r squared, and then we could add those together to have the surface area. Well, let's consider if we had a cone of radius capital R and of slant height right here, or it's also called lateral edge L. So if we take this cone and we see about unwrapping it to see what it looks like, so we're going to split it here and we're going to unwrap it, and as we do that we see that the material it would take, the surface area of this cone, is actually the sector of a circle. So it's a portion of a circle, and so when we take this cone and we unwrap it, we get this, and we can see that our lateral edge L ended up here and here, so those are both L's. But what is this arc length here for this piece of the circle, this sector of the circle? And this used to be wrapped all the way around here, and so this is the circumference of this original cone's base, and so that's going to be 2 pi capital R. Now, how can we find the area of this? Well, what we could do is we could compare it to a circle. We know the area of a circle and we know the arc length, or the circumference, all the way around the circle, so we could set it up in a proportion, and this area of this sector is going to be proportional to the area of the circle, pi L squared. If we'd gone all the way around, it's a circle of radius L, and then we compare it to this arc length, which is 2 pi r, compared to all the way around, which is the circumference, 2 pi L. Now we can multiply both sides by pi L squared. We can cancel the pi L squareds, we can cancel the 2's, the pi's, and one of the L's. So the area of this sector is going to be pi RL, where R was the original radius of the base of the cone and L was the slant height. Okay, but what if we had some other function we're rotating around here so that we generate this solid, and we're interested in the surface area of this solid? What are we going to do here? Well, we had this function. If we wanted to know from A to B, we know how to find the length of this function. We found that in the last section. We found that by making little line segments and approximating this, and then we let the number of little segments go to infinity. So what if we took a little approximating line segment here and we rotated it around? And if we did that, it would form a band here, because here's our little approximating line segment, and as it rotates around we would see we would have this band. Let's take this band, have a look at it a little closer. So we're going to just do some representative band on the interval, the ith interval. So we have x sub I and x sub I plus 1. Here is the edge. The curve is this blue. Our little approximating line segment L is here in red. And as we rotate this around, whatever this y value is here, that's our radius of this circle on this end, so we'll call that little r. And then we look at our function value over here, and that would be, we'll call that capital R. That would be the radius of the circle formed when we rotate this around on the other end. Now let's take this band and let's actually stand it up so we can kind of have a look at it here. So here is the band, big R, little r, and our approximating line segment right here, L. Now, how are we going to find the surface area of that? Well, let's turn this into a cone by extending those two sides. And we know how to find the surface area of a cone, but in fact, if you look here, if we found the surface area of this cone, and then there's also a cone right here, and if we subtracted off the surface area of this cone, we would have left the surface area of this piece. This is called the frustum of a cone when we chop off a cone like this. So we'll call that L sub 1, that length there. And so the area of the frustum is going to be the area of the big cone, which is pi r, and then this lateral edge, which is L sub 1 plus L, and then we're going to subtract off the surface area of this upper cone, which is pi little r lateral edge L sub 1. Now let's go ahead and distribute that r through, and then in order to simplify this, we're actually going to look at some similar triangles. We're first going to look at a triangle that would be right here, and we'll continue this down. So we have our similar triangles here. So we could take the hypotenuse out of the smaller triangle over the radius, and that would have to be proportional to the hypotenuse of the large triangle over the radius. So we're going to do that, and then we're going to clear this of fractions by multiplying everything by little r big R, and we would get this. Now, how that is helpful, we were trying to simplify this, and we have r L sub 1 in this, and now we know that r L sub 1 equals this, little r L sub 1 plus little r capital L, so we could replace it with that. We could then cancel these out, and then there is a capital L in common. Let's factor that out in front. Now the surface area then of the frustum of this cone, which is this little band, as we were rotating this little line segment that approximated the function around, could be found by doing pi times the length of that little line segment and then multiplied by the little r plus the big R, and those were the function values at the two ends of the band. Now, to make this a little simpler to express, we're going to take this, divide this by 2, and of course we've got to compensate for that if we do that, so we'll put a 2 here so that we have something that's equivalent. And this then is nothing more than the average of those two r values. So we're going to call that r bar, and it's going to be the average of little r plus big R. And so we could say the area of this frustum of this cone is 2 pi r bar L, where r bar is the average of those two radii from the two ends, and then our L is the length of our little line segment. So here we have that, and so we've got an approximate for the area of this piece of the function rotated around. It'll be an approximate of that on the ith interval. And now we can do a couple of things. We can choose a representative x on this interval and let our r bar then be the function value at that x. And we can also approximate the length of this curve then with this line segment like we did in the last section. So the area that's formed as we rotate this piece of the function between x sub I and x sub I plus 1 about the x-axis can be approximated by 2 pi. This is just the function value at our representative x that's on that interval, and then this is just simply our arc length approximate here and found from the last section. And now you can probably see where we're going with this. If we want to know the area of this entire solid's surface area from A to B, then we are going to sum up, for an approximate, we're going to sum up n of these little bands, and then we are going to let the number approach infinity. Here we've got our Riemann sum, and that will equal the surface area from A to B of this function. So it's 2 pi f of x and then the square root of 1 plus the quantity of f prime x squared dx. So as we look at this, if we generate a solid of revolution and we want its surface area and we're rotating around the x-axis, it's going to be this integral. But there's some different ways to express this. This f of x could be expressed as y, and we could also use Leibniz notation. So here's another way that it could be expressed. But also, when you think about it, this piece of this integral came from that arc length. And when we derived the arc length, it was based on the distance formula. So we had the change in y and the change in x there, and they are interchangeable. They could go in either place. If we were looking at that in the distance formula, we could do that in either order. So we could actually turn those around, and we could have dx dy here, and then we could have dy, and we would want to do this if we had x as a function of y. And then the other important thing to remember if we change these places is our limits of integration would be two values for y. So there's different ways that we can express this rotated around the x-axis. Now let's consider how would this be different if we were rotating around the y-axis. If we were rotating around the y-axis and we looked at our circumference of our circle, it wouldn't be 2 pi y, it would be 2 pi x. So here we have rotated around the y-axis, 2 pi x here. We can still leave this in terms of the derivative of this function with respect to x and dx and our limits in terms of x. We could still write this using Leibniz notation. We could still interchange the x and the y here if we had it as x as a function of y. And so if we did that, we've got to change our limits in terms of y, and we have dx dy here and dy here. Now notice then, rotating around the y-axis, all of these are x. So different ways we can do this depending on how we have these functions and for our situation. So the best thing to do is to do a sketch and have a look. So for example, if we had this function and we're going to rotate this around the x-axis and generate this solid and then find this surface area, we need to ask ourselves, if we rotate this around, we generate this circle, we need the circumference of this circle, and so this radius would be y. So this one would tell us that after our integral we would have 2 pi y. Now if we had a function and we wanted to rotate it around the y-axis and generate the solid to find the surface area, again we think of, if we were rotating around the y-axis, how our circle would be. We need the circumference of this circle, its radius then is x, and so for this integral, we'd have this integral, and then we would have 2 pi x, and then our square root and the rest of that. So important to draw you a little sketch to keep that straight. It's not if you're integrating with respect to x or with respect to y, it's how you're rotating. So everything that's rotating around the x-axis would have this 2 pi y, and everything rotating around the y-axis would have this 2 pi x.